Here we're starting a new section, a new topic, as we're going to introduce graph theory. And graph theory is a very practical and common tool used to solve application problems throughout computer science and in lots of other fields. But it's one that you'll run across a lot, especially if you're in the computer science field. You'll see graph theory used to solve all sorts of problems. So we're going to just get into kind of some basics of it. We'll see some interesting problems that you can describe using graphs, the way that we're going to draw them. For instance, when you use a GPS system or like Google Maps or something, there's a graph that's used to navigate and to draw your route. There are all sorts of problems like that. We're going to see a few of them as we get into just a very basic intro to graph theory over the next few lectures. So let me show you an example of a simple graph in the way that we mean. And these are not graphs like you've drawn in algebra classes or calculus classes necessarily. These are very specific kinds of pictures. So let me give you an example. If we model like a small network of train lines, rail lines, you might have a couple of cities here. Let's say here's Philadelphia, and then up here somewhere would be Boston, and then let's say New York is down here, and then DC is somewhere around here. And so you might have a train that has lines that look like this. And so if you wanted to travel from DC to Boston, for instance, you could travel along this line, and then along this line, and so on. And so you can map out this system. Now, interestingly enough, we're going to talk about how we could also draw this exact same graph this way, or many other ways. If I drew this right here, it looks like an entirely different graph, but it's actually the exact same graph. And my point here is just that where we physically draw these dots is not significant. Those dots we're going to call the vertices, or the nodes, and then we have edges that connect them, these lines that connect them. And so what's significant about a graph is just what nodes exist and what connections exist among them. So if you look carefully at these two graphs, you'll see that there's the exact same nodes, right? There's DC, Philadelphia, New York, and Boston, and then the exact same connections among them. Philadelphia and New York are connected, DC and New York are connected, DC and Philadelphia are connected, and New York and Boston are connected. So it's the exact same vertices, the exact same nodes, and the exact same edges, and so those two graphs are identical. So the way that you draw it is not significant in any way, other than just by choice, if you decide that you want to draw it a certain way. So you might want to draw it the way we do it on the left, just to emphasize sort of the geography of the situation, but it's not significant as far as the graph itself. The graph itself, it only matters what nodes there are and what connections there are among them. So that's kind of the basic idea. We keep the definition relatively simple, and the simplicity of it, kind of like we saw with set theory, helps us apply this very broadly. If it's a very bare definition, there's more chance that we can apply it to more things. So again, a graph consists of nodes or vertices. The singular of that would be vertex, and edges. So we've got nodes and edges. So the nodes are the vertices, these are the dots, the edges, these are the lines. And every edge, excuse me, every edge connects two nodes. Well, I shouldn't say two. Sometimes you can have a edge that connects one node to itself. You can have a loop, which we'll talk about later. But basically these edges are designed to connect nodes to one another. So some things you won't see on a graph, or you shouldn't see if the graph is correct. You won't see an edge that goes nowhere, right? So you wouldn't have, for instance, a node here and then an edge that goes out into space and doesn't connect to anything. That would not make sense. That would not be allowed on a graph. You also won't just have generally a node hanging out by itself. That is possible. You can have disconnected nodes. But for most of the applications that are interesting and most of the topics we're going to be looking at, you wouldn't see that either. But certainly an edge that connects to nothing, you shouldn't ever see in a graph. Every textbook that talks about graph theory has to start with the same story, so I feel obliged to start with that as well. And this is called the Königsberg bridge problem. The Königsberg bridge problem goes something like this. There was a city in Europe called Königsberg, and the residents of this city would sometimes go out and walk through the city, and the city looks something like this. If you sort of draw a map here, there was a river going through the city that looked something like this. So there was a couple of islands in the middle of the river, the main one here in the middle and then one kind of off to the right, and there were bridges spanning this river in a couple of places. So there was a bridge here, one here, and so on. And so as residents of the city would go out and they would kind of walk through the city, they would challenge themselves to try to walk across all these bridges and to create a path through the city to see if you can walk through the city and cross every bridge exactly once. So they asked the question, is there a way to design a path through this city, walking over every bridge, but only exactly once? So not recovering any ground, not going back across a bridge that you've already crossed. And so they go out and they try this. This is as the legend goes. Who knows if this was actually what they would do, but the legend goes that they would do this and they would have this as a pastime. And it turns out that Euler came along, the same Euler you've no doubt heard of in many other contexts. He came along and when presented with this problem, he started thinking about it and he realized that the map itself was not very significant. In other words, the exact location of these bridges was not really what was significant. What was significant was the locations they could be, the land masses, and the connections among them. And that's really what tends to be true about a graph theory problem, is when all that you are concerned with is some items, some locations, some people, some things like that, and connections among them. When that's the significant piece, you can abstract the situation down to a graph, which is a very simple abstraction, and it kind of cuts away all of the extra stuff that you don't really need. So what Euler did is he drew a picture that looked like this. He drew 4 dots to represent the 4 land masses. Now again, the actual locations of these dots is not significant in any way, other than this arrangement kind of gives you a sense of where they are. So this dot corresponds to this landmass here, this one is this island in the middle, and so on. But again, we could rearrange those in different ways, and it would be the exact same graph. So once he drew this, then he drew lines to represent bridges. So he said between the north side of the river and the island in the middle, there are 2 bridges, so he drew 2 edges between them. The same thing with the south of the river. And then there are bridges from each of those land masses out to this eastern area in the middle of the river. And so he drew this graph with 4 nodes and these 7 edges to describe this problem. And as he thought about this and as he worked on this problem, he started thinking about more and more sort of interesting conclusions he could draw about pictures like this, and thus graph theory was born. So that's the story as it goes. Who knows how much of that is true, but certainly Euler was the one who initiated this study and started thinking about the interesting conclusions you can draw when you start looking at a graph like this. So we're actually going to come back to this problem a little bit later, but At this point, if you want to sort of take this with you and think about this question, you can also look it up and find the answer, but it would be more interesting to think about if you could find a path like this and what that path might look like. So I'll leave you with that, and we'll come back to this question later on. But just quickly, covering a couple of basic definitions, simple stuff that is not all that hard to grasp. First of all, just the definition of a graph, and this is sort of the more formal definition. We're not going to need to use this much, but I just wanted you to see it once. So a graph, you can describe a graph, we'll call it G for an example. A graph looks like this, where it consists of two sets. So generally it's written this way, where there's kind of an ordered pair of these two sets. And having talked about set theory before, now we have a little bit of a background that we can rely on. We won't need it much, but you can have the set of vertices or edges, nodes, and then E, the set of edges. And each edge corresponds to one or two vertices. So there's a connection, and there are different ways to write down graphs if you want to write them down in this notation. More commonly, we'll generally just draw a picture. That's the most common way to represent at least a small, simple graph. If they get really complicated, it's hard to visualize them easily, and you'll have ways that you'll describe them maybe for a computer, for instance, using matrices or other options, which we may get into a little bit. So every edge has some correspondence with one or two vertices. If it's only corresponds to one vertex, that would be if there's a loop, so if it comes back to itself. Now we will only deal with finite graphs in this class, and most applications that I can think of would only have finite graphs, but in theory you could have an infinite graph. There's nothing in this definition that stops you from having that. A couple more basic definitions. You've got what's called a simple graph. The idea of a simple graph is basically one that has no loops and no repeated edges. So if you look back at our example here of the Königsberg Bridge problem, that would not be a simple graph. There aren't any loops, but there are some repeated edges. In other words, two edges that connect the same set of nodes, the same set of vertices. So that would be a simple graph. Another way you could phrase this, you could say that each edge connects two vertices, instead of just connecting one to itself. And then two vertices can only have I'll say up to one edge between them. A max of one edge between them. Of course, there can easily be a set of vertices that don't have a connection between them. So that's a simple graph. A couple of examples that I can draw for you of graphs that may or may not be simple. This one here, we have four vertices like this, and if I start drawing edges connecting them, so far that's a simple graph, but if I do something like this, that's no longer a simple graph. That would be what we call a multigraph. And the terminology multigraph just means that we're allowing multiple edges between the same two vertices. So multigraph. I could draw another one. like this. That would be a simple graph, right? There's no loops, and there's no set of vertices that have duplicate edges between them. So that one's simple. And then, of course, something like this, if you have, say, two edges like this, and then maybe you have a loop that comes back, that, of course, is also not simple. So the idea of a simple graph just means that it has no loops, no repeated edges. That's really all there is to it. So recognizing a simple graph is pretty simple. So depending on the application, a simple graph might be what makes sense in describing whatever situation you're trying to describe with a graph. And as we look at examples, and as you see examples on the homework, you can kind of think about whether it would make sense that these would be simple graphs or not. And then the last definition that I want to give you here real quick is the idea of a directed graph. Directed graph, also sometimes called a digraph, so it's shortened, but it's the idea of a directed graph. And all that it means is that edges have direction to them. So each edge has the idea of starting at one vertex and ending at another. Or maybe ending back where you were if you allow loops. So it's just the addition of the idea of direction. So I could have, for instance, something like this. If I draw this graph, that is not a directed graph, but as soon as I add direction to it, which we indicate with little arrows like this, then that is a directed graph or a digraph. So just the addition of this notation or this idea that there's a connection, a direction to the connections. And we'll look at a couple examples in the next video, and one of the examples we'll look at is a directed graph, and we'll think about what that means. So if there's a sense in which there's a directionality to the connections, you'd use a digraph. If you look back at the Königsberg Bridge problem, for instance, it's not a digraph because a bridge doesn't have a sense of direction to it. You can go in both directions. If you had one-way bridges or one-way streets, if you're drawing a map, then you would have a directed graph. So if you're building an application that has a map feature, so for instance, Google Maps, when they have a graph that describes streets and areas that you can, or ways that you can travel, they have to allow for the possibility of direction because there are one-way streets or one-way places that you can only travel one way. So again, depending on the application, it may or may not be necessary to allow for direction and to create a digraph, but if you need it, that's available as well. So there's just a couple of simple definitions. The definition of a graph itself, we're not going to use that technical definition very much. We're mostly going to use pictures to describe these and to think about them. And then the idea of a simple graph versus a multigraph and a directed graph. You'll see those terms crop up. You'll have some homework questions on them. And by the way, with directed graphs, you can also have directed simple graphs, and you can have directed multigraphs. So the same concept of simple versus multigraph can apply to directed graphs.